my teammate Dalton is going to pick up partway through and present. So this was a team of quite a bunch of us spread between here, virtual and in Australia. So that was already exciting. So our title of our presentation, Inertial Oscillations in the Marginal Ice Zone, and basically the question was, can we measure them from space? And so just some background on this. Inertial oscillations are sort of like a fun, quirky thing that exists in physical oceanography that are actually quite important. And so the idea is that if you imagine a wind picking up, so if a storm is passing by, then the ocean will have this sort of like wobbly response to it. And that's this like inertial response. And so this, you can imagine this is sort of what the velocity is doing. And if you project that onto a map view, you basically get these like funny looking moving currents. And one outcome of this is it creates these what are called internal waves that will propagate from the ocean surface into the deep ocean. And that's like one reason people care about these inertial oscillations in the first place, is these internal waves really connect the energy of the atmosphere to the interior of the ocean. And why we might care about them in the Arctic in particular is that as we have Arctic sea ice, this can increase the energy of these currents. And there's actually a potential positive feedback loop there. So the way that works is that as you have less ice, you can have more of this wind energy input to the ocean. That creates these stronger currents, that creates more mixing. And because the Arctic is sort of a funny place where there's actually warm water deeper down and cold water on top, that mixing will bring that heat up towards the surface, melt the ice, and increase this feedback loop. So it's really important to understand how these currents are changing over time. And there's some data from drifting fluid programs that show that these oscillations are becoming stronger. But it's just so hard to collect any kinds of observations in the Arctic. You need an ice capable ship, you have to put your instruments out, they might get destroyed by the ice. Really challenging and expensive to measure these sorts of things. So that was why we were motivated to see if we could develop another technique that might provide us a lot more data to understand how these currents are changing. And so our approach really draws from this technique called particle image velocimetry. And so the idea is you have a field of flow and you introduce particles to it, and then you can sort of visualize those particles. It's a little jumpy on the view, which is too bad. But by tracking particles in the flow, that's how you sort of can back calculate what the velocities are. And so our goal was to sort of draw inspiration from this technique, but apply it to satellite images and sea ice flows. So sea ice flows being sort of our particles that we can track, and satellite images being our large camera that lets us see what they're doing. And in particular, I was motivated to start working on this project because my group was involved in a cruise last year where measurements from the ship showed we saw one of these inertial responses. So that's this sort of like very classic, like wavy velocity basically that you're seeing here. And on board the ship, because they're operating in ice so much, they sort of have their own pipeline for pulling satellite imagery and looking at what's happening with the ice. And so when they sort of just put together their pictures that they were pulling, again, it may be really hard to see on the Zoom here, but you can see lots of clouds going by, but beneath that, you can see this sort of waviness that's happening in the ice. And so we decided this was maybe a good event to start with because we know this is happening. And so we'd like to, start with this, validate our method, and then try to look at a lot more satellite images to get a sense of how these currents are changing. So we learned a lot about satellite imagery. I'd say that's sort of one of our main takeaways. So the idea here is that we're taking advantage of these polar orbiting satellites. So you can see these sort of typical tracks. And you'll see that because they're sort of like slices that are crossing over the poles all the time, you're actually getting like a lot of images that are happening in high latitudes. So if you can combine all these different images together, then you actually have a really like high temporal resolution data set you can work with. But the trade-off is that to work with those images, you have to work with a relatively low-level satellite data product. And this was something that was new to all of us and something that we learned a lot about and also found to be really challenging. So just some of the things that we really had to deal with was just even understanding where and how to access the data, sorting through all of the spectral bands that are available at this level, dealing with the fact that these images are not sort of on any sort of common latitude longitude grid, but instead are sort of like just keyed into the satellite path. And so like a brief overview of our satellite image acquisition and processing was first you have to figure out even what product you need and where you can get it. And that seems like it should be pretty straightforward. But we already knew what satellites we needed. And even still, if you go sort of search for that instrument, you can see there's 400 different kinds of satellite products available for this instrument. So you first have to understand like, okay, of these 400, what do I even need? And then we found at least 4 different archives where you could potentially access these images, understanding like which is the best archive. And so we, with Alex's help, found that this Earth data archive seems to be really good for this sort of thing. It's really the only one that has data on the cloud that you could potentially work with directly without having to download. Then the second part was we need to actually load this data. We need to create composite images, like mix together all of these different spectral bands. We have to like zoom in on the areas we're interested in. We have to reproject the data to common grids, all of those sorts of operations. And for that, we use a package called SatPy. And we'll talk more about that. And then basically the idea is, okay, so finally we managed to create like these pictures that show, in this case, we can see ice, we can see clouds, and we can see ocean. And so this is sort of basically just like a photo that it took all this work to put together this photo. And then there's also other data products that are available that are more like a mask that'll show you where there's clouds, where there's ice, and where there's land, but they're really not at the sort of granular level that we need for this. But so thinking about how we can smartly combine these different kinds of data products to create better images that we could use for the tracking. So that's
1 minute.
Oh gosh, that was fast. I'm sorry. Dalton, I'm going to hand it off to you. To share.
All right, you can you can go to the next slide. All right, so we did use SatPy, which is this magnificent tool to read, manipulate, and write from satellite instruments. The next slide. The learning curve is realistic, but guys, remember there are sometimes tutorials that are really useful and we really benefit from them. Next one. We wanted to use OpenCV and we started some tests with it, but since we didn't, next one, sorry. But we were just not there yet because it's so much trouble and work to really get the satellite images to work, right? And then, well, what we did is we took this SatPy information, we produced this notebook, and then we got, next please. We got this image, right? It's this really nice image from it, and we don't have the time for the details, but next one, we were able to like put together some information from this like really high resolution satellite data, and SatPy is really useful. So I think we were in the right direction, but we simply don't have enough time to really go into all the details. But it was like pretty cool and interesting to get to this point. We want to finalize, Laura?
Yeah, so just some reflections from the two of us. As Dalton said, learning curve is steep. We were surprised that like some of these things were as challenging as they were. But doing this really taught us like how these data really work and what's possible with them. There's also good resources out there, but they're just hard to find. And even using them, you still really do have to understand what they're doing, and that just takes time to understand. But I think we're really happy the code we've developed should allow us, we've focused on this one region and time period, but it's just a couple lines of code that we can access any of these different data types for any time for any region. So that's something I think we can really imagine using in the future. Yeah, and our team was on 4 continents, and so trying to just stay coordinated using GitHub, sharing ideas, just staying on the same page when people are working overnight and during the day was super hard. And I would also just say thank you to everybody else on the team. Pitching this project was really outside of my comfort zone, and I really appreciate everyone thinking it sounded cool, and I think we learned a lot. So yeah.
Thank you. Do we have any questions? I have something a comment. As a satellite photographer, I completely feel the pain that you went through and everything that you described. I have not actually used SatPi. I'm curious, was it, you did the reprojections in SatPi? Did you do reprojections?
We
Mapping?
got to the point that we would have done them next,
Okay.
but we didn't get to
Because
it.
I normally do my mapping outside of Python.
Okay.
Bring it in. This is what it is.
Yeah,
But
yeah,
I'll have a look at it.
yeah, it definitely seems like it should be able to do it, but we didn't quite get there, yeah.
What were the 4 continents?
We were here, Brazil, UK, and Australia, and even within the US, 1 team member is on the East Coast, so.
That may be a new record.
So you sit there, this isn't actually about the science, but about the workflow, right? Because being across so many time zones, how did you do that coordination to, like, you accomplished a lot, it's really cool.
Yeah, it helped a lot that folks really pushed their time zones to work at uncomfortable times, so that from like, I don't know, like 8 AM to like 3 PM Seattle time, like most of us would be online. But even still, I think like I spent a lot of my time just trying to like know what was happening and like write it down. And so just because like also we were spending so much time like trying to figure out what we even need to do and just like making sure everyone is aware of like, these are the questions like we have, these are like what we think the answers are, and these are the resources that we found. So a lot of that was just like taking notes and writing it down. Yeah.
Okay, thank you. We